Welcome, everyone. It's an honor for me to be here. Thank you so much for inviting me to talk about two of my favorite topics and how they're related. So yes, my research area is in software architecture, and software runs our world. And it is generally not built well already. And now we're going to add this new concern of building software that is energy efficient. And so one of my concerns as a software architect, a software architecture researcher, is how to design for energy efficiency in addition to all the other things that we already want to design for, security and scalability and performance and usability and so forth. But also, how can we do this in a sustainable way? And by that, I mean the kind of dictionary definition of sustainable, which is able to maintain some level of quality or performance. And the fact is that software degrades over time. All software degrades over time. It's subject to entropy or rust or however you want to think about this. And so this is the second half of my title. I'll get into the myth of Sisyphus in a few minutes. So I'll start with a question. Is design hard? Is it hard to design a software architecture? The high-level design of a system? And the answer, like all answers to complex problems, is it depends, right? Yes and no. Novel design is hard. So take the Sydney Opera House. This was conceived and architected in the 1950s, and at the time, the structural engineering challenges of the Sydney Opera House were beyond what anyone had dealt with to that point. They were pushing the envelope of the possible. And so that design was hard. The Sydney Opera House, when it was finally completed, was 10 years late and 1,357% over budget. Tell that to your manager when he complains about your project. But the good news is most design is not novel. Most of us are not building the Sydney Opera House. We're building similar kinds of systems over and over again. So maybe there's hope for designing for energy efficiency, that maybe we can apply known design principles and primitives to do this predictably. That's what we want out of an engineering discipline. So is it novel to design for energy efficiency? And actually, mostly it is right now. And this is because we're not, by and large, teaching our students about energy efficiency. That's a problem. And so practicing software engineers don't know how to do it. They don't know how to think about it. They don't understand the design primitives, unlike designing for performance or security or maintainability, where we have at least some idea and students are being taught some of that. So is this a problem? Yes, this is definitely a problem. We need to change the way that we educate our software engineers because software runs our society and software is taking up an increasingly large percentage of the global energy pie. And so we need to be more responsible and more responsive in the way that we design software. So what do we do? And so following on Patricia's lovely introduction, we need tactics. Tactics are the most primitive design decisions that you can make when designing an architecture. So an architecture is a collection of design decisions, and some of those design decisions are made to do whatever the function of the software is. If you're designing anti-lock brakes, then they have to read sensors from the wheels and decide when to brake and how much. And if you're designing a transaction processing system for the bank, then you have to do whatever the system is supposed to do. That's functionality. But there's a set of other design decisions that we make to achieve the quality attributes of the system. How fast is it? How secure is it? How reliable is it? How usable is it? How testable is it? How energy efficient is it? And these decisions are called tactics. And these quality decisions are actually orthogonal to the functionality decisions, right? I can have a system, let's say for the anti-lock brakes, that's reliable or unreliable, that's fast or not fast, that's easy to maintain or hard to maintain. Those quality decisions are what we get when we make architectural design decisions, when we choose tactics. So we say that a tactic is influential in controlling a quality attribute response. So we have existing categorizations for the traditional quality attributes, things like availability and security. If you want to design a system that's highly available, I would certainly like my anti-lock brakes to be available when I need them, right? When I'm going into a skid. So I want to make sure that whoever's designing that system thinks about availability. So to do that, they have to think about how to detect a fault. How do you even know? How does your software even know that something bad has happened so that you can prevent that fault from turning into a failure? And then how do you recover from a fault? Maybe you have a standby component that takes over from the failed component. And maybe how can you prevent faults? And so we have collected and categorized these kinds of design primitives, these design principles, and these we found to be extremely useful in education, but also in design and analysis contexts. So tactics give us a useful vocabulary. They give us mental models for how to think about design and how to analyze designs. And I've been teaching software architecture for more than 20 years. And even when I'm teaching architecture to practicing architects, people who have been already developing software for a decade or 2 decades, they love these tactics because it gives them a structure, a way to think about the problem. Because design is hard. When you're faced with the blank page and you're told, go and design, make decisions, that's a really scary starting point. And tactics give you a kind of checklist approach. Well, how am I going to detect faults? How am I going to recover from faults? How am I going to prevent faults? Where do tactics come from then? Well, they come from looking at what architects do and have done over the decades in practice. So we interview domain experts. We set up workshops. We review the literature, the architecture literature. And then we've cataloged these. So Patricia, thank you very much, mentioned my book, Software Architecture in Practice. And in this book, we have cataloged 10 different categories, 10 different quality attributes, ilities, we sometimes call them. And we have to admit that this will never be complete. It will never be done, and so that's the bad news, because there is always going to be some evolution in the world of technology. But the good news is that, in fact, it's quite stable. We like to think of it as a kind of periodic table of design, that you don't expect new elements to appear very often, and in fact, they don't. So what are the tactics for energy efficiency? How do we help architects actually design for energy efficiency in practice? Right now, there's relatively little guidance. We don't have good curriculums. We don't have good textbooks on this. And so we did what I said. We derived a collection of tactics through a taxonomic systematic literature review. And for those of you that don't know what those words mean, essentially, if you think of what a botanist does, if a botanist is trying to discover new species of plants or animals, they might march through the rainforest with a bag over their back and collect samples from the forest floor and look at the properties of those samples. These are plants with thick, broad leaves, and these are plants with tall, spiky leaves. And then we would associate those properties. We would, first of all, look at the commonalities, group them into families, and then associate them with properties. The plants with the broad leaves are good at collecting rainwater and surviving in low-light environments, and maybe the plants with spiky leaves are good at surviving droughts, and so forth. So we do the same thing with the tactics that we distill from the literature. We look at their commonalities, and we come up with a categorization. And so this is the categorization for energy efficiency. This is what we can use to teach our students and to design and to analyze designs. And this was motivated in part by the work of Professor Lago. So there are tactics for resource monitoring. How do you know how much of a resource you're using? If you think about driving your car, a lot of cars these days have tell you your instantaneous gas consumption, right? You're tooling along the highway at 90 kilometers an hour and you're only using 4 liters per 100 kilometer, and then you hit the gas, or you go up that steep hill, and all of a sudden your consumption goes up to 14 per 100 kilometers. Well, we need the same kind of ability so that software can respond to different loads and perhaps reconfigure or change its performance characteristics. And so we use resource monitoring to figure out how to allocate resources. And there are different strategies for that, how you can allocate more resources in an efficient way, and also how you can scale down, something that also we tend not to teach. When we teach scalability in computer science, we teach how to scale up. But for energy efficiency, scaling down is at least as important. And then we need to have software that can adapt to different resource conditions. So for example, if your system is a group of services or microservices, you may need some kind of brokering or adaptation to figure out what are the best coalitions of services to use to achieve the best energy outcomes at a given time. So what can we do with tactics? As I said, these can help inform architectural design. They give people a starting point. They give people a framework in which to reason. They can also be used if you're looking at the design decisions that have already been made or that are being proposed. So they can be used as an analysis technique, an analysis checklist. You can use them to adapt or improve existing systems. So we published a paper about 3 years ago where we looked at a big collection of Android apps, and we showed how by applying one of those energy tactics, we could tweak those Android apps so that they used, on average, 30% less energy. So these things work. And we can use them to create reference architectures for the entire domain. Great. Are we done? Mission accomplished. Problem solved. No, some of you are shaking your head. Yeah, sadly, no. And this gets to the second half of the title of my talk, The Myth of Sisyphus. So for those of you not up on your Greek mythology, Sisyphus was a Greek king who angered the gods, and in particular angered Hades because he cheated death not once but twice. And so Hades punished him by forcing him to roll a rock up a hill every day, and just as he was about to reach the top of the hill, the rock would roll down to the bottom again. This is the life of every software maintainer, right? And this is just the nature of software. Software always accretes technical debt. So to begin with, design is seldom done well, and even when it is done well, it gets worse over time, this entropy notion. So here's an example from my own experience, just so you don't think I'm dissing other people's software. This was a system, architecture of a system that I built with a grad student more than a decade ago. And we picked this nice, simple, layered architecture with 5 layers. And we developed the system. It was a visualization system for doing flexible visualizations. And then one day we decided to reverse engineer the code that we had built. And this is what we had actually built. There were these extra dependencies, the dark lines there, which undermined the intent, undermined the evolvability of the architecture. We had used this nice, simple model with very few dependencies between the components so that it was easy to change parts of it independently. And what we actually implemented violated that. And this is the best possible case, right? We were the architecture people. We consciously chose an architecture pattern to begin with. There were only 2 developers, really 1.1, because the grad student does most of the actual work, and we still got it wrong. So this is my picture of the state of the practice of software development, right? Most developers are this poor guy, working like crazy to implement a feature or to resolve a bug, but in fact incredibly hampered by the legacy of the code, the leaky boat that they're being forced to pilot down the river. So some recent examples, just from the last few weeks. This is very timely for me. Southwest Airlines had a huge outage, system outage that caused, you can see thousands of flight delays costing them almost $1 billion in lost revenue. And then about 2 weeks after that, an FAA system had a major outage that disrupted air travel for several days. And in both cases, if you look at the articles, they blame these outages on out-of-date, unmaintained software that had accumulated way too much technical debt. Well, all we have to do then is educate our developers to not do this, right? Wrong. And I don't say this with any happiness, but let me tell you a sad story. About 10 years ago, I ran an experiment where we developed a software design course. We taught this course over a semester. We taught the students software design concepts, patterns, and tactics. And at the end of the semester, they were given a project. They were given the design for the project, and they were told to implement it. And that design used the patterns that they had been taught all semester long. All of the students, and we did this at 3 different universities, all the students correctly implemented the system. That's to say the functionality was right. But over 3/4 of them, 78% to be precise, violated the design. And they violated, like the example that I showed you with my system, in ways that undermined the design, that would make it harder to extend, harder to modify in the future. That is not sustainable. And it gets worse because we thought, well, all we have to do is tell the students, raise their awareness, and they will see the error of their ways and fix it. And we tried techniques where we asked the students to reflect, self-reflection. We did peer review, where one student would review another student's design. We did instructor-guided review. And in most cases, the students still didn't see it. They did not understand the consequences of their implementation decisions that degraded the architecture. I think a sad story. Okay, what about tools? There's a whole bunch of technical debt detection tools out on the market. So isn't this a solved problem? Just point your tools at it, like SonarCube or Designite? Sorry. It's not a very happy talk, is it? So we did another study last year where we looked at various popular technical debt detection tools and compared their results. And what we found that they disagreed about the most basic measures of a software system, like the number of lines of code in a file. They couldn't even agree on that. And to make it worse, okay, even if they disagreed slightly, if they were still giving useful insight, that might be okay. But in fact, when you boil down all of the insight that they're giving, all they're telling you really is big files are bad. We knew that already. You can do that a lot more cheaply as well. One tool, however, did provide useful results, this tool called Deviate. And Deviate focuses on not the code, but the architectural flaws. Well, of course, the architecture is embedded in the code, but it focuses on design-level flaws. And these flaws are highly correlated with the things that cause that poor guy in the boat to be slowing down: bugs, changes, and churn, effort. And so just to give a quick example, and then I'm done with this talk, one case study that we did using this tool was we looked at a communication platform created by a Canadian company called Bright Squid, and we took a snapshot of their system. We analyzed their code base and their revision history, all the changes that they had made. We looked at that over a 1-year period. That was the before state. And then we used this tool to identify all the architecture problems, all those improper dependencies. And based on that, they created a refactoring plan to remove some of those dependencies. And then we analyzed the after state. So you don't need to read this whole chart, but the whole point is the flaws were reduced. So there was the before state and the after state, and their refactoring actually did remove many, not all, but many of these design flaws. And what happened is, as a result of this refactoring, we got really dramatic productivity improvements. It's like somebody patched the holes in the boat and bailed out the water, and all of a sudden they could make forward progress again. So the average time to close issues was reduced by 72%. The number of bugs they needed to add to the code to fix a bug on average was reduced by 2/3, and the amount of time to fix a bug was reduced by 30%. So tools to the rescue, actually. Lessons learned. In my experience, with appropriate guidance, we can help architects design for any quality attribute, and energy efficiency is the newest quality attribute that we've added to that list, but all of the existing strategies seem to work equally well for energy efficiency. The bad news is that this software, these tactics will incur technical debt. Like every software design decision incurs technical debt. Yes, even your software. Because without effort, without adding some energy in the form of refactoring, all designs degrade all the time. So this is a Sisyphean task, right? You're rolling that boulder up the hill, and it's going to fall down again. So we can do something about it, though. So I am ending the talk on a positive note. That with appropriate analysis, with appropriate tooling, we can sustainably achieve sustainability. All it takes is some attention to architecture integrity. Thank you.